Welcome. My name is Marketa and today we're gonna be diving into support vector machines, or SVMs for short. If you have any questions, don't hesitate to contact me on my via mail mlap@viuc.dk. By the end of the series of these next couple of videos, you'll have a solid understanding of the theoretical side of SVM, their use on different types of datasets, how to classify data that is non-binary, how kernels work and when we should use them, and finally, how this all looks in practice using scikit-learn. Support vector machines, I will be in general using SVM as an abbreviation, is a supervised learning algorithm, which means that it learns from the labeled training data to classify new and unseen examples. It is optimally used for small to medium-sized nonlinear datasets, and we're talking in hundreds and to thousands of instances. In this particular video, we will be looking into linear classification. The next one will go over nonlinear classification. However, SVMs can also be used for regression as SVR, so support vector regression, and novelty detection. However, this is not going to be covered in this series, but if you are interested in it, you can go and check out the book Hands-on Machine Learning with Scikit-learn, Keras and TensorFlow in chapter 5. So first, let's look into the simplest way or simplest form of using SVMs, which is on linearly separable data. In our examples, we will be looking into flowers. We want to tell which one of the genus of iris flowers it is, whether it is the versicolor or the setosa flower. They look very similar. They are both the same shape and same color. However, they differ in the size of their petals. Our data will be in 2 dimensions, so the petal width and the length of the petal. So as we can see, these 2 flowers are clearly separable in this particular dataset, and there is an infinite amount of lines that we can draw between them such that they are separated. So you can see the red and the purple line are edges, or the maximum and minimum, and we can draw any line in between those and separate the 2 datasets so that they are not touching. However, some of these or most of these will not be an optimal separator, so we want to separate the data such that we maximize the margin between the 2 classes. And you can see that on the right image. The margin is the distance between the hyperplane and the closest data points, which are called support vectors, which are the 2 highlighted ones. The gutter, or it can also be called the street, is showed with the dashed line, and SVM tries to find such a separation so that the gutter is as wide as possible. And the distance from the support vector, so the highlighted one, to the line, the hyperplane, will be referred to as the margin. Now I'm talking about hyperplanes a lot. For those that are not familiar with the term, hyperplane is just a general term for any dimension that we can be talking in 2 dimensions. Hyperplane is just simply a line. If we were in a 3-dimensional space, then it would be a plane. But to generalize over any dimensions, we will just be using the term hyperplane. Mathematically, a hyperplane is defined as the dot product of W, which is the weight vector, and X, which is the input feature vector, plus the bias W0. If the data was perfectly separated, so everything on one side of the hyperplane, it belongs to one category, and everything on the other side belongs to another category, then we can say that one side it will be smaller than 0, and the other side strictly bigger than 0, as the hyperplane is the one that is equal to 0. That is it for the hyperplanes. Now, as we are talking about SVMs, it is important to note that they are vulnerable to scaling. As you can see on the example on the picture, which is the same data, but one is unscaled and one is scaled. So pre-processing might be needed in order for optimal performance of support vector machines. That is it for our first bit on SVMs. I hope this gave you a clear understanding of the basic concepts of SVM. If you have any questions, you can drop them in the comment section, and I'll see you in the next one.